the long run, we'd like to be able to make calculations related to the motion of an object without always having to rely on drawing a graph. So what we'd like to do now is take a look at what we know from certain graphs and see if we can come up with general equations or formulas that we can follow every single time without having to always graph things out. So in order to come up with these equations that we're going to use, we're actually going to start with a velocity time graph. And just keep in mind that the area below the slope is equal to the object's displacement. From there, if you're so inclined and you're looking for a bit of a challenge, you can go through the next bunch of steps that I've laid out on the first page of the note from there. What that's doing is using some information that we're getting from this velocity time graph and some other things that we talked about earlier in the unit, and whittling it down to try and come up with specifically 5 key formulas that we can use in more general situations. I'm going to go over that in more detail in class, though, because what's more important is to be able to use those formulas to actually solve problems. So I'm going to skip over where these equations come from in this video and focus just on how we actually use them. Then when we get into class, I'll talk more about where they actually come from and explain that first page of the note in more detail. In the end, we arrive at 5 key formulas that we can use in many different situations, specifically the kinds that we'll see throughout the last chunk of this unit. It's really important to note, first of all, that when we are using any of these equations, we need to make sure that our units always stay in what we call our standard base units. So that means that our time should always be in seconds, velocity should always be in meters per second, acceleration, therefore, will end up being in meters per second squared, and to make all of that fit together, we need to make sure our displacements are in meters. So we'll keep all of that in mind, and then from there, let's take a look at what this chart is telling us. So one thing you'll notice about the chart is that it doesn't have any vector symbols on it, and it also doesn't have any delta symbols on it. Technically, if we wanted to be completely correct, we would need to include those delta symbols and those vector symbols. But when we're using these equations, it becomes a little bit painful to write those every single time. And so for the purpose of this course, when you're using these specific equations, it's okay if you don't include the vector symbols or the delta symbols either. So with those removed, as long as we still remember that displacement, velocity, and acceleration are all vectors, we can write out the formulas as so. But we need to make a little distinction. First off, the very top equation is a little bit different than the others. It's the one that can only be used, and there's a special note down below the chart on that, it can only be used in situations when the object is undergoing constant velocity. Because if you notice, it doesn't say anything about acceleration, and it doesn't say anything, for that matter, about a v1 or a v2, because terms like v1 and v2 are things we use when something's changing its velocity. And of course, there can't be any acceleration either, because that would mean that it's changing its velocity. So this equation can only work and only make sense when we've got 0 acceleration, something moving at constant velocity. If you recognize that something is actually moving with an acceleration, then you've actually got some options. Any of these 4 equations are ones that could be used in any situation when there is an acceleration involved. And specifically, the kinds that we're going to deal with in this course are situations when the acceleration rate is constant. So the speed is changing, but the rate at which the speed is changing stays the same throughout, stays constant throughout. And you'll notice that we do have 4 different ones we can use. So why do we need so many different ones? Well, this gives us some useful tools depending on what situation we're put in. So for example, if we just look at the very first of those 4, it uses acceleration, it uses v1 and v2 on top, and it uses time on the bottom. So this would be a useful equation to use if, let's say, we didn't know anything about displacement, and we also weren't even asked anything about displacement. So in that case, it'd be useful if we could just ignore displacement completely. It's not given to us, and we don't need to find it, so we should find an equation that uses just the other 4. And so A equals v2 minus v1 over t would be a perfect equation to use because it connects together v1, v2, a, and t. And notice that I could use that for any combination of those 4 variables. So maybe in some cases, I know v1 and I know v2, and I already know the acceleration. In that case, I could use it to find time. Or maybe I know time and acceleration in v2, and I could work backwards to find v1, for example. So we need to select the correct formula based on which 4 variables are going to be involved in our equation. That includes the given and the required variables that we're looking for. And then from there, we can just plug in and solve. So we'll now see how we can actually use that in a full problem-solving example. And this is now your first real go at taking a stab at a full problem-solving situation. And when we solve problems like this, there's a specific method that I'd always like you to follow. And specifically, it's called the GRASS method. And GRASS actually has 3 S's in it. GRASS method. That word GRASS then becomes an acronym to remember these 6 important steps that we should follow with every solution that we go through. So, G, that first G, stands for given information. So any information that you were given in the question, that should be stated first. And that just helps you take stock of what you're dealing with, what you're working with to start with. Along the way then, as you're reading the question, you should be able to figure out what are you required to find. So make note of any required information, which is usually what's the final answer that you're looking for. From there, though, once you know the given and required information, you can take a look at something like a formula sheet, or for now you can look up at your chart, and try and figure out what the appropriate formula would be. That's what the A stands for. Appropriate formula. Once we find that appropriate formula and we write that down, then we can perform a substitution, meaning we just plug in our numbers in place of that formula. Once we've subbed all those in, we can do the actual solution part, where we maybe use our calculator if we have to crunch all those numbers. And then once we have a final solution, we need to summarize it all with a statement, which is another way of saying our therefore statement, to summarize everything. So just to divide things up, I'll put a little line down there, and now we can actually start our problem-solving process. So specifically in this question, we're dealing with a car that's accelerating at 0.8 meters per second squared, does that for 4.5 seconds, and eventually reaches a speed of 130 kilometers an hour. And we want to try and find how far does the car travel in this time. Well, the first thing we need to figure out is the G, the givens. So what is given to us? Well, the first thing we are told is an acceleration rate. So we can write down what A is equal to. It's 0.800 meters per second squared. We are also told how long it takes. So rather than calling it delta t or anything like that, I'll just call it t, and that's 4.5 seconds. We're then told that it reaches a speed of 130 kilometers an hour. So if it said that it started at that speed, that would be like a v1, but it says that it reaches that speed. So that would imply that it's doing it at a later time or at the end. So that's really a v2 that we're being given. And v2, I'm going to write down it as it's given. It's 130 kilometers per hour. But in the end, I'm going to need to put that into meters per second. So we can talk about this in more detail in class, but a quick shortcut that you can use, and just take my word for it for now, is to divide that by 3.6. If you have something in kilometers per hour, if you divide it by 3.6, that gives you a shortcut to immediately change it to meters per second. So just to keep an extra decimal place, I'm going to call it 36.11 meters per second. That 3.6 is a way of dealing with 2 different things at once. So you are converting the kilometers to meters and also converting hours to seconds all in one quick calculation, which I can go over in more detail in class. That's all the information we were given in this question, but we now need to think about what are we required to find. Well, it says how far, and how far means it's some measurement of length. Or in our case, in kinematics terms, we would say it's displacement. So we are looking for D. How many meters has this thing actually displaced itself? From here, we just need to select the appropriate formula. So we can actually do this by taking stock of what we've just listed in terms of givens and requireds, which in this case connects these four variables together, A, T, V2, and D. And now we can look back at something like our chart and figure out what equation puts those four together. So if I look closely, I see that there's an equation here that uses displacement and V2 and acceleration and time. So this must be the equation that I need to select in this particular case. I can now use that appropriate formula that I found. So I'll start by just rewriting it. D is equal to V2 multiplied by T, and then subtract 1/2 times A times T squared. That's my appropriate formula. Now all I have to do is substitute into it. And in this case, I'm okay if you don't include units in this intermediate step, as long as you make sure that your final answer has the correct units. So just using brackets, I'll say this is 36.11, then time is 4.50, subtract 1/2 times 0.800, and then 4.50 for time again, but that one needs to be squared. So don't forget about that squared at the very end of that formula. It's a very easy thing to forget. At this stage, though, it's just calculator work, so when we plug all that in and churn it all out, we get approximately 150 meters. Now that we have done all this work, we've done our substitution and we've solved, so we create a final therefore statement that says, therefore, the car has traveled about 150 meters. And I just said about because we did round it off. So we'll try one more example, but we'll go a little bit quicker through this one. So now we've got a cyclist that's traveling 12 meters per second and needs to come to a stop at an intersection. It's able to stop in 5 seconds, so we want to find the acceleration of that bike. Well, again, we start with the given things. What are we told in this question? Well, it says at the very start that the cyclist is traveling at 12 meters per second. So if that's how the question starts off, that's a good indication that that's a starting velocity, or a v1, an initial velocity. 12 meters per second, and in this case, because it's already in meters per second, we don't need to make any conversions. We can also make note that the time it takes for all of this to happen is 5.0 seconds. Eventually, we're going to try and find acceleration, but if we're going to use any of those formulas from our chart, we need at least one other given piece of information. It doesn't seem like there's any other specific numbers given, but there's a little hidden piece of information. It says that the bike needs to come to a stop. And so if something comes to a stop, that's a velocity of 0. So the v2, the final velocity, must be 0 meters per second, because that's what it means to come to a stop. So those are the three that we know. And then there must be some fourth that we're trying to find, which, as the question specifically states, must be acceleration. So now we have a different collection of 4 variables. We have v1, v2, time, and acceleration. Well, if you go back up to your chart and take a close look at all the options that we have available to us, the only one that puts all 4 of those variables together is the one that is A equals v2 minus v1 over t. So from there, we just need to substitute in the things that we just wrote down. We just have to be very careful when we do it. So remember that the v2, even though it's the thing that comes first, the v2 is actually the 0 meters per second, and the v1 was the 12.0 meters per second. And then I divide by 5.00 seconds. And so when that happens, I'll just insert an extra little step, which you can skip over if you want to, but just to be clear on what's happening. Keep in mind that the top of this now is going to become negative. So it's actually negative 12.0 over 5.00. And when that happens, it means that our final answer is going to be negative as well, specifically negative 2.4. And remember, that's an acceleration, so that's negative 2.4 meters per second. And anytime you get a negative answer, you should always stop and really take a good hard look at it. Sometimes a negative answer might mean that you've done something wrong. For example, if you get a negative value for time, we don't really deal with negative time, and so you know that there must be something that went off track. Here, though, you have to ask, does it make sense that this acceleration is a negative value? And it does make perfect sense because we know this thing is actually slowing down. It's starting at some velocity and coming to a stop, and we've already talked about how if something starts with a positive velocity and slows down, it must have a negative acceleration. So that's our substitution in our solution, but it's really important that we state a final therefore statement as well, especially for a question like this. Because that negative sign has a specific meaning to us. When we see that negative sign, we know that it means the object is actually slowing down at that 2.4 meters per second squared rate. So that's something we should communicate to someone else who's reading this solution. So here's how I'm going to write it. I'm going to say, therefore, the bike is slowing down at a rate of 2.4 meters per second squared. So notice in my answer there, in my therefore statement, I didn't call it negative 2.4 meters per second squared because the rate, just the amount of acceleration, is the 2.4. I'm dealing with the fact that it's negative by stating in words that it's slowing down. So if your acceleration is negative 2.4 meters per second squared, it means that you are slowing down at a rate of 2.4 meters per second squared. So that's just giving a little bit of extra explanation as to where that negative sign comes from. The final example I want you guys to think a little bit about and try, and we will take up in more detail in class.